Welcome to this explainer. Okay, today we are decoding something absolutely fascinating. We're going to look at how we take our messy, everyday human intent and translate it into strict, machine-readable instructions. If you've ever wondered how your basic problem-solving logic turns into actual computer code, well, you are in exactly the right place.
It really all starts with one fundamental question, right? How do you teach a machine to solve a human problem? Because programming isn't just about typing a bunch of abstract syntax on a screen. It's really simply bridging that gap between how we intuitively solve problems every single day and the highly specific step-by-step logic that a computer actually needs to take action.
So, here is our roadmap for today. We're going to start with the problem-solving lifecycle, then move into the basics of program data, and tackle operators and sequential logic. After that, we'll get into problem-solving with decisions, and finally wrap the whole thing up with the power of modular programming. Let's jump right into Section 1, the problem-solving lifecycle. Basically, understanding how we humans use logic. Before we write a single line of code, we really have to understand how we, as humans, process problems. And there are 6 essential stages to making a smart decision. First, we identify the problem. And then we have to thoroughly understand it, like getting down to the root causes. Next, we figure out alternative ways to solve it and critically pick the absolute best way from those options. Only then do we list out the specific step-by-step instructions to actually execute that solution. And finally, we evaluate the result. Skipping any of these steps, like, say, not truly understanding the problem or completely ignoring alternative solutions, almost always leads to a terrible decision and a lot of wasted time. Let's bring this down to earth with a super relatable example. Task number 1, making a cup of coffee. You literally do this life cycle every day without even thinking about it. You identify a problem. You're tired. You understand you need caffeine. You identify alternatives, right? You could brew coffee, buy coffee, maybe drink tea. You select the best way, let's say making it at home to save some cash. You follow your own mental instructions to brew it. And finally, you evaluate the solution by taking a sip. See? You are already a highly logical problem solver. Moving right along to Section 2, the basics of program data. Time to learn the vocabulary of computers. Now that we've got human logic down, we need to transition to the raw vocabulary that a computer actually understands. Data enters a computer as just unorganized facts, so we have to explicitly tell the machine what type of data it's looking at. For example, we've got integers, which are just whole numbers, like 1, or negative 376. Then there are floating point numbers. That's how we handle decimals, like 3.45. Next up, characters. These store a single value, like the letter A or a hash symbol. And finally, strings. A string is just a collection of characters shoved together, like the phrase, "Hello world." By assigning these types, the computer knows exactly how to handle the information.
So, where does all this organized data actually go? Well, it goes into a variable. Think of a variable as a name for a specific memory location used to temporarily store data. And the cool part is, its value can be changed and reused. They're basically like temporary storage boxes living inside the computer's volatile internal memory. But here is the absolutely crucial thing to remember. Each box holds only one value at a time. If you pop a new value into that variable box, the old value is completely destroyed, gone. Now contrast that temporary box with a constant. Just like it sounds, a constant is a specific alphabetical or numeric value that never ever changes while a program is running. Once a constant is assigned a spot in memory and given a value, like let's say you're calculating the area of a circle and you set the number pi to 3.14, it is permanently locked in for the entire execution of that program. No overwriting allowed.
Okay, on to Section 3, operators and sequential logic. This is where we start actually processing our program data.
So we've got our data beautifully boxed up in variables and constants. But how do we tell the computer to actually do something with it? Enter operators. Mathematical operators tell the computer exactly how to process numeric data. You definitely recognize the common ones, like the plus and minus signs. But in programming, notice that we use an asterisk for multiplication, a / for division, and a % sign for something called modulo division, which is a really handy tool that just calculates the remainder after you divide something.
Now, the really crucial point here is how the computer reads a whole combination of these operators. Computers are huge sticklers for the rules. They process math in a very specific, strictly ordered way.
If it's evaluating a complex expression, it handles the math inside the parentheses first. Then it moves on to multiplication and division, and so on, stepping down through the math sequentially until everything resolves into one single resultant value, say the number 24. It's this beautifully structured, totally predictable sequence.
And that strict order brings us perfectly to the most basic building block of programming, control flow, sequential instructions. This is just a set of statements that compulsorily execute one after another without any overlap, based entirely on their textual order. It literally just means the computer's going to execute line 1, then line 2, then line 3, completely unconditionally. It doesn't skip a single step.
You can actually map this out to see how simple it really is. Whether you're looking at a written algorithm, a flowchart, or pseudocode, this sequential logic structure is literally just a straight, downward-pointing line of instructions. It just flows predictably from one step to the next. It is the absolute simplest logic structure out there, and every single coding problem uses it, either all on its own or as the baseline for much more complex operations. Which leads us to Section 4. Problem solving with decisions. Time to introduce some branching program logic. Because let's be real-world problems aren't always a straight line, right? Sometimes the computer actually has to make a choice. To program decisions, we use relational operators. These are operators like equal to, greater than, or not equal to, and they allow the program to evaluate a specific condition. The fascinating part is that the result of a relational operation is always a logical data type. It simply evaluates to either true or false, which, in computer speak, just translates to a 1 or a 0.
Let's see how this decision-making builds on what we already know. We have our straight-line sequential logic, but when we introduce a decision logic structure, things get interesting. In a flowchart, a decision is represented by a diamond shape. That diamond evaluates a condition using those relational operators, and it creates branching paths. The program is going to execute one specific set of instructions if the condition turns out to be true, and an entirely different set of instructions if it's false. It's essentially a fork in the road.
Now, once we start creating all these different paths and blocks and branching decisions, keeping track of our data becomes absolutely critical. That's where variable scope comes in. You have local variables, which are declared inside a specific block of code. They are temporary and super safe because they avoid naming conflicts. Once that specific block finishes running, the variable is dumped from memory. Global variables, on the other hand, are defined outside of all functions. They hold their value throughout the entire program. But because global variables can be accessed from anywhere, you have to use them with extreme caution so you don't accidentally confuse the computer and overwrite important data.
Finally, Section 5, the power of modular programming, breaking down massive complexity.
We've looked at tiny sequential instructions, and we've looked at branching decisions. But how in the world do you build massive, complex software from just those little pieces? We do it through modular programming. This is a software design technique where a huge, overwhelming program is broken down into small, independent, and interchangeable parts called modules or functions. By isolating tasks into these little modules, your code becomes infinitely easier to read, test, and scale up. If you need to fix a bug, you just tweak one small module without risking bringing down the entire program.
A really great way to visualize this is the top-down approach. You start with a massive, highly complex problem at the very top, and you systematically decompose it downward into multiple smaller parts. And you don't stop there. You keep breaking those modules down into even simpler modules, creating this massive hierarchy until you finally reach program logic that is so incredibly basic, it just can't be broken down anymore.
To tie this all together, we use a process called stepwise refinement. This perfectly mashes up our original human problem-solving lifecycle with this new modular design. You start with your big initial problem. You break it into general steps. Then you break those into really detailed steps. You just keep repeating this refinement process until your logic is so incredibly specific that it's ready to be written out as pseudocode. And from there, you just translate that pseudocode into real, runnable computer code. We literally refine our messy human logic down into pure, structured machine instructions.
Which leaves us with a really empowering thought to wrap up this explainer. Think about it. If a computer program is really just everyday human logic, translated into tiny, structured, sequential modules, what complex, real-world problem are you going to break down next? Thank you so much for joining me today, and I really hope you leave here ready to apply these problem-solving tools to whatever challenges you're facing. Catch you next time.